Hi, sorry I'm a little late about getting this lecture posted. Had to go out and shovel the driveway a few times today. Um, the I'm posting this up on YouTube, and I'm breaking the lecture up into two separate short videos. I think the lecture would be normal than the typical 50 minutes that we actually spend in class, but one of the advantages of watching it on YouTube is that you can watch it at 1 1/4 speed or 1 1/2 speed. Of course, you can pause at any time to catch up. I recommend having a piece of paper as we're going through the video, and then pause the video at a couple points. You have the option to actually work some stuff out, and then proceed with the video. So we're going to talk about start talking about some particular distributions that you'll encounter with discrete random variables. Uniform distribution is probably one of the more common ones, and then right behind that is what's known as the binomial distribution. So there are three characteristics of a binomial experiment. So there are a fixed number of trials. Trials are repetitions of an experiment, and we use the variable n to represent the number of trials. And there are only two possible outcomes called success and failure for each trial. We let the letter P denote the probability of success, and the letter of Q the probability of failure. And you have to have either a success or a failure. So P plus Q is equal to 1. So if you know one, you know the other. If P is equal to 0.7, Q is equal to 0.3, for example. And then the other condition is that for a binomial experiment is that the n trials are independent and are repeated using identical conditions. Because the trials are independent, the outcome of one trial does not help in predicting the outcome of another trial. So the classical binomial experiment is, the coin toss experiment, that you toss a coin 100 times. You're interested in the number of times that maybe heads occurs. That would be your success. So n would be 100. If it's a fair coin, P would be 1/2, Q would be 1/2, and then the number of heads would be the random variable that we're interested in, and it has a binomial distribution. But this appears in a lot of other cases as well. You can use it to actually model, even if you, in digital electronics, if you're concerned with the value of a binary bit, and it may be either 0 or 0 or 1 if you consider that to be a random variable. And then you look at 50 bits, and you're interested in any random pattern of 50 bits. How many of those bits are 1? Again, that can be modeled as a binomial experiment. Another way of saying the trials are independent is that for each trial, the probability of success and the probability of failure remain the same. They don't change from trial to trial. For example, randomly guessing at a true-false statistic question only has two outcomes. If a success is guessing correctly, then a failure is guessing incorrectly. So this is an example from the book. It says, suppose Joe always guesses correctly on any statistics true-false question with probability P equal to 0.6, then Q is equal to 0.4. This means that for every true-false statistics question, Joe answers his probability of success and his probability of failure remain the same. I don't think that's really a good example of a binomial experiment. I would hope that any student would apply some knowledge they have out of the course to guessing problems, and they're going to know more in one area than another. Hopefully you're not guessing at all, but you kind of get the idea. So the outcomes of a binomial experiment fit what's known as a binomial probability distribution. I talked about this briefly in a previous lecture. The random variable x is the number of successes obtained in n independent trials. You'll sometimes see this written like this: x and then tilde BNP. The BNP represents a binomial experiment with n trials when the probability of success is equal to P. And that's read as x is a random variable with a binomial distribution. So here's a simple example. I talked about the coin flipping example. So a fair coin is flipped 15 times. Each flip is independent. What's the probability of getting more than 10 heads? So in setting this up, X would be the number of heads in 15 flips. In any experiment, X could take on any of the values between 0 and 15. With a fair coin, we would expect maybe to get something closer to 7 heads in any given trial. But it is possible that we might do this experiment and actually get 15 heads in one particular experiment. Since the coin is fair, P is equal to 0.5. And Q is equal to 0.5, and the number of trials N is 15. In this particular case, we're interested in the probability that X is greater than 10. Another example is we have a fair 6-sided die, and we're rolling it 10 times. And we want to find the probability of rolling a 1 more than 3 times. So write out the values for each of these. What is our random variable? What is N, the number of trials? What's P equal to? What's our probability of success? And what's Q equal to? And then we're interested in what particular probability. So pause the video, take out a piece of paper, and write down your answers to these, and then come back and restart the video. I'll give you a second. Okay, so let's look at the answer to these. X would be the number of times that a 1 is rolled when we roll this die 10 times. So we could get, between 0 and 10 ones, when we carry out this experiment. So the number of trials is 10. Now the probability of success here is our probability of rolling a 1 on any particular trial, and that's 1/6. So the probability of failure of not rolling a 1 is 5/6. So we're interested in the probability that X is greater than 3 according to the problem statement. So I'm going to stop the video at this point, take a little break, allow you to take a break, and then we'll come back and finish this lecture up. I've got about, I think about 6 more slides. I want to talk about evaluating these probabilities, and then also talk about the cumulative distribution function.